So how did we actually get from thinking the Earth was this, fixed center of everything to knowing we're on a planet going around a star?
Right. It feels so incredibly obvious to us now.
Yeah, but someone had to be the very first person to say, hey, maybe we're the ones moving.
And imagine saying that thousands of years ago. It went against everything people saw, everything they felt under their feet.
Exactly. So for this deep dive, we're going way back. We're looking at the person credited with that first leap, Aristarchus of Samos.
Ancient Greek astronomer, a mathematician. And we're digging into the sources we have about his life, his world, and these, frankly, revolutionary ideas he had.
And our mission today, especially for you listening, is to pull out the core stuff about Aristarchus. We want you to get a real sense of who he was back then.
Yeah, what did he propose? Critically, how did he figure it out with the tools he had?
And why did his biggest idea, heliocentrism, why didn't it stick back then?
Okay, so let's start with the basics. Who was Aristarchus?
Right. When and where?
He lived roughly 310 to 230 BC, so a long time ago.
Very long ago, and born on Samos.
Born on the island of Samos, yeah, it's in the Aegean Sea. And this is deep in what historians call the Hellenistic period.
Okay, Hellenistic period.
Yeah.
Yeah, that's after Alexander the Great, right, when Greek culture was spreading everywhere.
Exactly. After Alexander's conquests, Greek language, science, philosophy, it exploded across the Mediterranean, the Middle East. It was a dynamic time.
A time of, big new cities, more trade, more mixing of ideas.
Definitely. And Samos is an island, but the sources suggest he didn't just stay there. It seems likely he moved to Alexandria.
Alexandria in Egypt. Now that was the place to be then, wasn't it?
Oh, absolutely. Alexandria was the intellectual capital of the world. Think the library, the museum. It was drawing scholars from all over.
Like the Silicon Valley or, the main research hub of the ancient world.
That's a great analogy, is where the cutting-edge science and philosophy were happening. He wasn't working in isolation.
Okay, so he's in this vibrant environment. Did he study with anyone significant?
Yes. Apparently he was a student of Strato, of Lampsacus.
Strato. Does that name ring a bell?
Well, Strato became the third head of the Peripatetic school.
The Peripatetic school. The Aristotle school.
The very one. So this tells you Aristarchus was trained right in the heart of the dominant scientific tradition. He knew the Aristotelian physics and cosmology inside out.
Which makes it even more amazing that he proposed something completely different.
Exactly. It makes his big idea even more significant.
And that big idea, let's get to it. Heliocentrism.
Heliocentrism, the first known proposal that the sun is at the center.
Sun-centered. It sounds so simple now, but just imagine. Everyone, philosophers, regular people, they all knew the Earth was solid, unmoving.
And then Aristarchus comes along and suggests, no, the sun is stationary at the center.
And the Earth?
The Earth goes around it, in a circle, once a year. And on top of that, the Earth spins on its own axis once a day.
Wow, that just turns everything upside down. Where did he get such a radical idea? Was it totally out of the blue?
Well, probably not totally out of the blue. He seems to have built on some earlier threads.
Like what?
Like Anaxagoras, who'd suggested the sun wasn't a god, but maybe a hot rock, maybe even a star itself. Aristarchus supported that idea.
Okay, demystifying the sun a bit.
And then there was Philolaus, a Pythagorean thinker. He proposed a central fire, that things moved around.
Ah, so Aristarchus might have taken that abstract central fire and said, wait, maybe that's just the sun.
That seems plausible. He gave that central position a concrete, observable object, the sun.
That's a huge conceptual leap. But how do we even know he proposed this? You said his main book on it is lost.
It is lost, sadly.
Yeah.
Which is, a common problem with ancient sources. We often rely on later writers quoting or describing earlier works.
So who tells us about Aristarchus's heliocentric model?
Our key witness is another giant, Archimedes.
Archimedes of Eureka fame.
That's the one. In his own book, The Sand Reckoner, which is about calculating huge numbers, by the way,
Really?
Archimedes specifically mentions Aristarchus and describes his book of certain hypotheses.
And what did Archimedes say those hypotheses were?
He lays it out pretty clearly. He says Aristarchus hypothesized that, quote, the fixed stars and the sun remain unmoved, that the earth revolves about the sun on the circumference of a circle, the sun lying in the middle of the orbit.
That's incredibly direct. Sun fixed, stars fixed, Earth moves around the sun. Couldn't be clearer.
Nope. It's unambiguous heliocentrism.
But okay, if you propose the Earth is moving, you immediately hit a big problem, observationally speaking.
A big one, stellar parallax.
Right. If the Earth is moving in this big circle around the sun, shouldn't nearby stars seem to shift their position slightly against the background of very distant stars over the course of a year?
Logically, yes. That apparent shift is parallax.
And using just their eyes, no telescopes, they looked, and they saw nothing. The star patterns seemed constant all year round.
They saw no parallax. And this is a major argument against a moving Earth for centuries.
So how did Aristarchus handle that? Did he just ignore it?
No, and this is another point where his thinking was just remarkable. He didn't back down. He reasoned, well, if we don't see parallax, it must be because the stars are just unbelievably far away. So far that the Earth's orbit is like a tiny point compared to that distance, making the parallax shift too small to detect.
Whoa, wait. So to save his heliocentric model, he had to basically inflate the size of the universe massively.
Massively. Unimaginably larger than anyone thought. The stars couldn't be just points on some nearby celestial sphere anymore. They had to be incredibly remote. Maybe, as he hinted supporting Anaxagoras, there were other suns, just incredibly distant.
That's brilliant reasoning, using the lack of evidence to deduce something huge about the cosmos itself.
It really is. It turns the objection on its head. The universe isn't small enough for us to see parallax. It's vastly bigger.
Okay, so that's the lost heliocentric work known through Archimedes. But you mentioned Aristarchus does have one surviving book.
Yes, his only one that made it down to us is called On the Sizes and Distances of the Sun and Moon.
Sizes and distances. Sounds practical.
It is. But here's the puzzle, the paradox we mentioned.
What's that?
In this book, all his calculations, all his geometry, it's based on a geocentric model, Earth at the center.
Wait, what? After proposing the sun was the center? His surviving practical work assumes the Earth is. Why?
Well, we can only speculate. Maybe heliocentrism was still a hypothesis he was playing with, not yet something he used for everyday calculations.
Or maybe the geocentric model was just the standard way everyone did astronomical calculations back then, like the common language.
That seems quite likely too. To communicate his methods for measuring sizes and distances, he might have stuck to the familiar framework everyone understood, even if he personally suspected a different underlying reality.
Okay, that makes sense. So working within that geocentric framework, what did he figure out about sizes and distances? How did he do it?
He used some really clever geometry and observation. To estimate the sun's distance relative to the moon's, he looked at the moon during its half phase, first or last quarter.
Half moon. Okay, why then?
Because at that exact moment, the sun, the Earth, and the moon form a perfect right-angled triangle with the right angle at the moon.
I see. So if you're on Earth and you can measure the angle between the sun and the half moon?
You can use trigonometry. Well, the geometry they had then to find the ratio of the Earth-Sun distance to the Earth-Moon distance.
Brilliant idea. What angle did he measure?
He measured it as 87 degrees.
87 degrees. And the real value?
Is very, very close to 90. About 89 degrees and 50 minutes, almost a right angle itself from Earth's perspective. That 3-degree difference in his measurement, likely due to instrument limits,
Yeah.
it had a huge effect on the result.
So what did his 87-degree angle tell him?
His calculations showed the sun was about 18 to 20 times farther away than the moon. Let's say roughly 19 times farther.
19 times farther, when in reality it's...
It's about 400 times farther.
Wow, okay, so numerically way off. But still, the method itself was groundbreaking, right? The first real attempt to quantify that distance?
Absolutely. The geometric thinking was sound, even if the input observation wasn't precise enough. And that incorrect ratio actually stuck around for a long time. It also implied a solar parallax of about 3 degrees, which was also incorrect but influential.
Okay, so that's distance. What about size? How did he estimate the size of the moon and sun compared to Earth?
For that, he turned to lunar eclipses.
Watching the Earth's shadow cross the moon?
Exactly. He observed how wide the Earth's shadow seemed to be compared to the moon's diameter as it passed through, and how long the eclipse lasted.
And what did that tell him about the moon's size?
From those observations, he estimated the moon's diameter was roughly 1/3 of the Earth's diameter.
1/3. How close is that?
That's actually pretty good. The real value is closer to about 27%, so 1/3 isn't far off at all. Much better than his distance estimate.
Okay, so moon is about 1/3 the size of Earth. How did he get to the sun size from there?
He used that distance ratio he'd calculated, the sun being about 19 times farther than the moon, and combined it with another key observation, that the sun and the moon look almost exactly the same size in our sky. Their apparent angular size is nearly identical.
Right, you can cover the sun with the moon during a solar eclipse.
Precisely. So if two objects look the same size, but one is 19 times farther away,
then the farther one must be 19 times bigger physically.
Exactly. So Aristarchus concluded the sun's diameter must be about 19 times the moon's diameter.
And since the moon is about 1/3 Earth's diameter,
You multiply 19 by 1/3, roughly, and you get that the sun's diameter is about 6 or 7 times larger than the Earth's diameter.
6 or 7 times wider than Earth. Again, we know the real number is much bigger, like 109 times.
Right, way off in absolute terms. But the implication was monumental.
That the sun is huge compared to the Earth.
Yes. Even with his inaccurate numbers, his calculations showed the sun utterly dwarfs the Earth, and that finding actually looped back to support his heliocentric idea.
How so?
Well, think about it. Does it make more sense for this gigantic sun to orbit the tiny Earth, or for the tiny Earth to orbit the massive sun?
Yeah, intuitively, the big thing should be the center. His own flawed size calculation argued against the Earth being central.
Precisely. It added a kind of physical logic, a sense of scale, to the geometric argument for heliocentrism.
That's really interesting how the different pieces of his work connect, even with the inaccuracies. Did he do anything else besides these big cosmic theories and measurements?
He was practical too, it seems. We hear from Vitruvius, the Roman architect and engineer, that Aristarchus designed sundials. He's credited with inventing or improving two types, a flat one, like a disc, and a hemispherical bowl type called a scaphe.
So he wasn't just a theorist, he was applying his astronomical knowledge to practical things like timekeeping.
Seems so. A theorist and an instrument maker.
Okay, so we have this brilliant thinker proposing heliocentrism, calculating cosmic scales, designing instruments. Why wasn't his heliocentric model just embraced immediately? Why did it take, 1800 years until Copernicus?
Well, several big hurdles. As we said, it contradicted everyday sensory experience. We don't feel the Earth whipping around the sun or spinning.
True, the common sense argument.
Then there was the physics problem. Aristotelian physics, the dominant system, said heavy, earthy things naturally belong at the center and tend to fall towards it. A moving Earth didn't fit that framework.
Right, it needed a whole new physics, which didn't come until much later.
And that lack of observed stellar parallax was a persistent scientific objection. Without seeing it, it was hard for many to accept the Earth moved.
What about the idea that maybe his views were seen as, impious or against the gods? There's that story, isn't there? That he got in trouble for it.
Yes. That story seems to be a long-standing misunderstanding, actually.
Oh, really? It wasn't suppressed for religious reasons.
The evidence points differently now. Modern scholars, looking closely at the sources, particularly a passage from Plutarch.
Plutarch, again, writing centuries later.
Right. In Plutarch's account, it seems Aristarchus was actually joking. He apparently suggested that someone else, Cleanthes, a Stoic philosopher who opposed heliocentrism, should be the one charged with impiety for wanting to mess with the cosmos by disagreeing with Aristarchus.
Wait, so Aristarchus was ironically accusing his opponent of impiety?
That seems to be what Plutarch originally wrote, a kind of academic jab.
Yeah.
But somewhere along the line, maybe centuries later in a transcription or printing, the grammar got twisted, maybe accidentally, maybe influenced by later events like Galileo's trial. And it ended up sounding like Aristarchus himself was the one being accused.
Wow. So the whole narrative of him being persecuted for his ideas might just be based on a historical typo or misreading?
It largely seems that way. The main reasons his idea wasn't adopted were scientific and philosophical inertia. The weight of Aristotle, Ptolemy's later very successful geocentric system, and the observational issues like parallax. Not so much religious persecution in his own time.
That completely changes the picture. So the idea just didn't gain traction then?
Not widely, no. Although, interestingly, about a century after Aristarchus, there was another astronomer, Seleucus of Seleucia, who apparently did champion heliocentrism. He reportedly treated it as a definite fact, not just a hypothesis, and even tried to find physical proofs for it. But his work is also lost.
So the idea flickered, but didn't catch fire until Copernicus much, much later.
Exactly. And there's still debate on how much Copernicus knew directly about Aristarchus's model, though he did mention him in an early draft. But Aristarchus was undoubtedly the first known proponent.
And science today remembers him for it.
Oh yes. There's the Aristarchus crater on the moon, a really bright, prominent one. There's a minor planet named after him. And the Aristarchus telescope in Greece. He's recognized as a pioneer.
Okay, let's try to tie this all together. What are the big takeaways for you listening to this deep dive on Aristarchus?
I think we see this incredible example of a mind working in a sophisticated scientific culture, the Hellenistic world, yet daring to think completely outside the box.
Using the tools he had, observation, geometry, to ask huge questions and make quantitative arguments. even if the precision wasn't there yet.
Right, and tackling major objections like the parallax problem, not by giving up, but by proposing an even more radical idea, a vastly larger universe.
And why does this ancient history matter now? Why should you care about Aristarchus today?
Because his story is just such a powerful illustration of how science progresses. Sometimes the biggest leaps forward go against everything that seems obvious, against common sense, against established authority.
It shows that revolutionary ideas might take centuries, even millennia, to be fully appreciated and accepted.
Exactly. It demonstrates the power of reason and mathematics to probe reality, even when our senses or current tools fall short. And it's a great reminder that challenging the status quo, even when it's difficult, is absolutely crucial.
It definitely puts the long journey of astronomy into perspective. We've gone from Samos to Alexandria's intellectual ferment to this startling heliocentric idea, his clever measurements, and the long wait for his ideas to finally prevail.
And maybe a final thought for you to consider. Think how incredibly hard it must have been to argue against not just the experts, but what everyone saw every day. The sun moving across the sky, the solid feel of the Earth.
What widely accepted idea today, something that feels like bedrock common sense or established science, might look completely different from a future perspective. What might be our generation's geocentrism?
A provocative question indeed. It certainly encourages you to keep exploring, keep questioning.